So welcome to this fourth lesson. In this lesson we shall examine the statistical response of a system with respect to perturbation, mainly limited to linear regimes. Let us start from a very simple example in a model in equilibrium of an harmonic oscillator. It means we have a representation of a polymeric spring, which, as we shall see, is equivalent to a one-dimensional easy model without coupling. And then we are looking to the study of how the system behaves when it is stimulated. So the statistical model of a spring, better, of a polymeric rubber band is essentially one in which we have a certain number of units that can stay elongated or contracted. So essentially, the model is like that of something that stays either like this or simply all messed up. And then with a certain force, it can be elongated. Clearly, in general, there are some van der Waals forces that keep the things together, but in this approximation, we neglect completely the forces that keep the things together. So we have just two states. State, say, one in which the system is crumpled, and state -1 in which the system is elongated. And we have an external, say, force, in this case, just a weight attached to the end of this chain. And we shall see that this is an isothermal model. We shall see at the end why it is called isothermal. So clearly, we have to define the magnetic field, which is essentially these things here. So the mass of attached to the spring, the gravity acceleration, which is just a constant, and the coordinate y, which is essentially the sum of elongated and minus contracted items. Clearly, there is a constant which is an influence for the behavior of the system. I choose to have a -1 and 1 in order to stress the analogy with the magnetic system or the Ising model. Clearly, here we do not consider the kinetic energy, so it will be an overdamped harmonic oscillator. Then you know that we have to compute the partition function of the model from which we can derive all quantities. And this is quite simple because we only have the external magnetic field, so we don't have any coupling between the pair of units, and so we can essentially sum over the number of ones, inserting the multiplicity of the configuration given by fixing the number of ones, the magnetization essentially. And clearly this is essentially the binomial. So when we factorize this constant part, we have just the expansion of the binomial, and so essentially we have this power 1 plus exponential of 2 beta mg. Then we can obtain the average position of the end of this chain by deriving the free energy, the logarithm of the partition function, with respect to the magnetic field, in this sense the mass attached to the string. And so this is the formula, and it is quite easy to derive this expression, which is again the standard magnetization of the one-dimensional easy model without coupling. Clearly, we can alternatively just compute the sum of the product of y times the probability of getting a certain position y, a certain magnetization again, which is simply given by the Boltzmann factor. And if we plot the average value of the endpoint as a function of the forcing, as a function of the magnetic field, essentially, we get this S shape, which is essentially an hyperbolic tangent. And we see that around zero, it means for small forcing, we have essentially a linear behavior, which is usual of almost any system. We have to design a system really making some effort in order not to have a linear response for a small variation of the forcing. We have seen that we are assuming isothermal environment. It means that we keep the temperature constant. But clearly, when we extend or compress the spring or the rubber band with respect to the initial position, we have a different. We have to either communicate heat to the external environment or absorb heat from the external environment. And clearly, if this is instantaneous, we can say keep temperature constant, and so we have an isothermal environment. But if we introduce heat conductivity, for instance, coupling any system to other, say, other variables that can transmit heat, then the conduction of heat behaves like a damping dissipation term, so that smaller conductivity slows down the relaxation. Then we can also introduce dynamics, and in order to do this, we can say essentially introduce a Monte Carlo simulation, because there is no dynamics intrinsic in the model. But we can do this, as we have already seen, by, say, introducing a transition probability between two spin systems that in general differ only by the flipping of one side. And so we can get this Markov chain equation, which gives the evolution of the probability of getting or serving a certain configuration at a certain time, given by a balance between the two fluxes, those coming from S prime into S, and those going from S into S prime. And as usual, we are interested in this case, time behavior of some observable, which, for instance, is the magnetization, which is equal to the average value of the spin, so the average value of one spin. Clearly, this system is homogeneous, so the average of any spin is equal to the magnetization, and which can also be defined in this way. And then we can say manipulate a bit this expression. So this time derivative depends on the time derivative of the probability. So we can insert here the Markov chain equation, which can also be, say, moving this sk into the summation reformulated in this way. Clearly, now that we are summing over S and S prime, we can also relabel the variables. So one of them can be labeled as prime, essentially in order to have the same transition probability from the two parts. And so putting all together, we see that the variation clearly of the magnetization depends on the acceptance rate of a change in the sign of some spin. And clearly, in this case, the change is just the flipping of one spin, and we know that we can flip any number of spins that we want, but in general, the greater acceptance rate is when we just flip one spin, because essentially the idea is that there are so many high energy configuration with respect to low energy configuration, to which we are in general interested in, that flipping a lot of spin in generally brings to configuration that have too high energy, and so they are discarded. And so let us suppose that only one spin is flipped, and so finally we can write this evolution in this way. So it essentially it is an average of sk times the transition probability. And now we have to insert the explicit form of this transition probability, which, since we are interested in a dynamics that brings to the equilibrium configuration, has to be proportional to the ratio of the asymptotic distribution. This is a sufficient condition to ensure that asymptotically the evolution goes towards equilibrium. And since we are again using isothermal simulation, so the temperature is the same, the partition function can be simplified. So essentially this ratio is just the exponential of the difference in the energy. Then we can now insert the explicit form of the Hamiltonian, and so this is the result for the ratio of the two asymptotic terms. In which case this is equal to this, except for the spin k, which is flipped. Now we have to choose one of dynamics. The simplest for the analytic goal is the heat bath recipe, and that says that the probability of having a certain spin depends on the form essentially like this. And clearly we can now exploit the fact that S is equal to plus and minus 1, so that we can so essentially bring this S here outside the exponential, since when S is equal to minus 1, this cancels out, and this is equal to e to the minus w. When S is equal to plus 1, this cancel out, and this is equal to e to the w. And so combining them, we get that we have a cosinus, a hyperbolic cosinus of w plus s times the hyperbolic sinus. You can check that if you put s equal to 1, you get the sum of cosinus and sinus hyperbolic, and otherwise we get the difference. And so finally, by putting all things together, we get this expression for the transition probability. And now we have to take the average value multiplied by sk. So this is 1. We can multiply sk by this, keeping in mind that this is always equal to 1. We get this result. And so essentially this is the result that we get. This is the equation. So essentially this is the magnetization. So by substituting, we have this linear equation for the evolution of magnetization. This is asymptotically this is 0. So asymptotically this is the m equal to hyperbolic tangent of beta h. So this is essentially m of infinity. And so we can also get the explicit formulate time dependence of magnetization, which is simply this one. Clearly for t equal to 0 we have m0, and for t equal to infinity we have the hyperbolic tangent of beta h. And this can be useful, for instance, to estimate the time needed to let m arrive to a given fraction of the asymptotic magnetization. So inserting a fraction f and then deriving when the time for which the actual value is less than a fraction f to the asymptotic value, we get the explicit expression for this waiting time. And essentially this is the expected relaxation time from for a Monte Carlo simulation to approach the asymptotic state. In order to be convinced, I wrote a simple program, and I both numerically integrate the previous equation and also simulate the behavior of a simple easing model for a 1024 chain with certain temperature, thermal field and temperature, which are condensed together, and a given out of equilibrium initial magnetization. And one can see that there are clearly fluctuations, but simulations agree perfectly with the estimated time behavior. Now, let us skip to the how a real harmonic oscillator, I mean, in this case, we also insert the inertia term, how an harmonic oscillator react, which is a very simple model, reacts to an external perturbation. So the equation for the harmonic oscillator is this one, to which we add an external forcing. At the beginning, we are just repeating what you already studied for the resonance of an harmonic oscillator. So if we add a periodic sinusoidal forcing, it is quite easy to derive the asymptotic solution, which is a function that oscillates at the same frequency with a given dephasing and also a given response to the perturbation. We can plot both the amplitude, which is this red curve here, and the phase theta, which is this one. And so you see that when omega is equal to omega 0, we have the largest response, which diverges if gamma is equal to 0, because when omega is equal to 0, this factor here diverges, while the phasing angle at resonance is pi over 2. So they are in quadrature when they there is a maximum response. While if this is quite far from the resonance, the phasing is essentially zero. Okay, but let's try to work a bit on this solution. So in general, for any form of the perturbation, especially if periodic, we can reuse the previous result using Fourier transforms. So just to remember, these are the transform, the anti-transform of a function that passing from the time to the frequency domain. Now, inserting this into the equation for the harmonic oscillator, we get a linear relationship between the, the, the amplitude of the transformed force, the mass, which is just a constant, and the damping and the difference between the natural frequency and the forcing one. So essentially, this is the relationship, and so we can see that the Fourier response is linearly linked to the amplitude of the Fourier transform of the forcing by a complex susceptibility term that so chi tilde of omega, which is the quantity that you want to investigate. So it is useful also to derive directly the response in the time domain. And so instead of working transforming the function, that the forcing function in the frequency domain, we can instead essentially decompose the forcing as a number of delta peaks, which is a green function representation. So the effect of one delta function at time t equal to 0 is that of communicating an impulse. So we can just solve the equation starting with a given velocity, the impulse, the effect of the impulse, and the position equal to 0. And now we set m equal to 1 just not to have this constant. And so if we look for the solution of this of the equation for the harmonic oscillator with these initial conditions, we get this expression here, which can be seen as the forcing, the amplitude of the forcing, times a response function. Now, if we Fourier transform both of these, we see that the response function is the Fourier anti-transform of the complex susceptivity. So clearly, we can also express the result of an arbitrary, in some sense, set an arbitrary excitation by decomposing the excitation as a series of delta function. Since we are interested at time t, the delta function is at time t minus tau times a response for from the interval tau integrated clearly to all previous intervals, or integrating from the time 0 to the time we are interested in, depending on how this function f is shaped. We are essentially assuming that it started perturbating at time 0. Now, passing to Fourier space, this is just a convolution between the response function and the forcing. It means that in the Fourier space, the Fourier transform of our system, of the response, is given by the product of the Fourier transform of the forcing times the complex susceptibility, and this is why we are interested in this complex susceptibility. Now, the real part of the susceptibility is this one. Remember, the susceptibility was 1 over this plus the part that depends on the damping times I. And so essentially we have squared, so made real the denominator, and this numerator appears. So this is an even function because the real part for minus omega is the same as omega, depends only on omega squared. And if we plot this function for several values of the damping gamma, we see that it tends to become so this is essentially the derivative of a delta function that goes from minus infinity to plus infinity in just a short interval, centered about plus or minus omega 0. Now, here the response exactly at the resonance is 0, but this is only when there is some damping, because if we put gamma equal to 0, we see that this part simplifies, and we have an exponential, an infinite response. So only when the response, the damping is not 0, we have this behavior. And essentially, what happens is that even if the harmonic oscillator has a frequency omega 0 equal to the forcing omega, but it has some dissipation, then actually the resulting frequency is not that at omega, and so there is a dephasing, and this dephasing is amplified by this response. So it is dephased negatively if the frequency is less than the actual one, and positive, and this brings to this pi over 2 dephasing at resonance. Okay, the imaginary part that we shall see is extremely important. Now is an odd function that has a peaks at plus or minus omega 0. When gamma goes to 0, clearly this becomes two delta functions, and this is how it is plotted. Okay, now if we look at poles of the susceptibility, they are minus I gamma plus or minus this square root of the difference between omega 0 square and gamma square. And clearly, depending on the sign of this difference, we can have two cases. The case of underdamped motion when omega 0 square is greater than gamma square. So essentially, this is positive, so the square root is real. And so we have two poles with a real part, but with a negative, all with a negative imaginary part. So they are both in the lower half of the complex plane. So if this is the imaginary part and this is the real part, they are, say, one here and the other here. While the overdamped motion is when this part is negative, so this is also imaginary. And in this case, the two poles are on the negative part of the imaginary axis. So essentially what happens practically for the response is that when we have underdamped motion. The reaction is that of reaching the asymptotic state, oscillating with an exponential damping. When the motion is overdamped, there is only the exponential damping without oscillations. In any case, the poles are in the negative imaginary part of the complex plane. And we shall see now, in this case, we have got this result explicitly, but we shall see in the following that this is a consequence of the fact that, for causal reason, a perturbance cannot affect the system in the past, but only in the future. And so essentially the response function is 0 for negative intervals and something positive, so positive, negative, something different from 0 for the positive time interval. So again, these are just a numerical integration of the equation of motion. We can see an example of an underdamped response which goes to 0 with an exponential damping but oscillating. And here is an example of an overdamped response in which there are no essentially oscillation. And these are the plot of the corresponding susceptivity. Okay, an important computation that we can do with the damped harmonic oscillator is the power W absorbed by the system. The power is just the product of the derivative, the velocity, derivative of the position of the oscillator times the forcing. And so since this is given by the response function, in this case I integrated from minus infinity to infinity, and so essentially, which is not really important because we are taking the derivative, we get this. Clearly, if we now replace this one with its Fourier transform, we can perform explicitly the derivative, getting this factor minus I omega. Here we have again the forcing that we can also replace by its Fourier transform. So essentially, this is the power in Fourier space. So we have 2 times the forcing functions multiplied by these exponential complex exponential factors time these complex susceptibility with multiplied by the imaginary unit. Okay, so let's suppose for simplicity that we are driving the system with a periodic and real force, so say cosinus omega t. In this case, clearly we can express it as a complex exponential, but we have to remember that this is just a real part. So the Fourier transform is the sum of 2 delta function, one at so centered at about minus omega and one centered at about plus omega, essentially because the real part is just e to the I omega t plus with a factor e to the minus I omega t, which are once Fourier transformed 2 delta functions. Okay, so now we can insert this form into the computation for the power, which was this one. Here I just copied the previous expression. And so inserting here the delta function, we have two here, two complex imaginary functions, two complex exponential functions, and again the same two imaginary exponential with multiplied by the suscettivity. Clearly, now we can perform all kind of multiplication, and if we now average over cycle, essentially we if we explicitate, we get these things here, and this part cancels out because they are oscillating functions, and so finally we only get this part here, and you notice that this is the difference between the two imaginary part, and so which has a different sign, and so essentially they sum together, and so we see that the absorbed power depends on the imaginary part of the complex susceptibility. And so this is an important aspect that will be exploited near the end of this lesson. Okay, the results we have gotten them in general, but they are valid also for our damped harmonic oscillator. We can verify it directly. So the time derivative of the response function that we wrote before is explicitly in the time domain this one, with theta is this tangent arc or inverse tangent of this expression. We can just work in the time domain, multiply by f the forcing cosinus, averaging we have clearly the square of this cosine, and then this part cancel out because it is essentially the sinus of 2 omega t, but this is an oscillating function, so cancel out. Now we can replace this cosine here, working a bit with this tangent inverse tangent function with this expression here, and so the average of cosinus is 1/2 that have lost somewhere, but at the end we get this expression here, and we can recognize here the imaginary part of with 1 omega, essentially. The other omega comes from this multiplication. The imaginary part of the susceptibility, looking in the previous slides. So essentially we confirmed, also working in the time domain, the result that we got using Fourier space. Okay, now let's pass to a different argument, Kubo formula, which is interesting because it allows, or it is derived by applying the concept of random motion to a generic thermodynamic quantity. So the idea is that for finite systems, all thermodynamic quantities, like for instance our model of a spring, follow a kind of driven random walk. So they oscillate, and if there is a common forcing, they have a drive plus oscillations, as we did in the simulation of the relaxation to equilibrium of our model of a spring. So let us try to derive the consequences of this analogy between any thermodynamic quantity and a driven random walk. Let us start without a driven part, without the given part, only with fluctuations. In this case, the Fokker-Planck equation is just this diffusion equation, which, as you know, gives the displacement that grows like T. As we already did, we can obtain the same result by computing the time evolution of the variance, essentially. So, no, this is just the definition of the expectance value of S square. Now we can take the time derivative and equal to the second derivative with respect to x. This second part can be integrated by parts, assuming that the p and its derivative go to 0 faster than x to the minus square. We obtain this result, which is essentially how the variance grows in time that we already derived before. Clearly, this holds only when t is sufficiently large, because the Fokker-Planck equation is not is a description for large times. Okay, on the other hand, if we start from the definition of position as the integral of the velocity, we can also write that s square is the product of two of these integrals, and so we can deriving one of them, we get this relation here, and averaging over the statistical ensemble, we see that the evolution of the variance, time evolution of the variance, essentially is given by the velocity autocorrelation function. And this is essentially the main point of the QO formula. Clearly, at equilibrium, they are invariant for time translation, so essentially this autocorrelation only depends on the time interval with respect to a given instant that we can call v with 0. And thus the evolution of the variance is this one. And so we can now insert the previous result and get these interesting results. So if we compute at equilibrium the velocity autocorrelation function, we get a way of estimating the diffusion coefficient. So essentially, we have related transport quantities and correlation functions. And we can extend this idea to other quantities. So let us now switch to linear response, which will bring us to the fluctuation dissipation relation. Okay, the idea is again the same. We examine what happens for delta peak perturbation, and we expect a response that depends on some response function that here I indicated as a key, since we have already seen that the response function is the anti-transform of the complex susceptibility. And clearly, this is just a repetition. We can see the perturbation as a series of delta peak. Clearly, I can perturb the system either keeping it in equilibrium and then bringing it out of equilibrium, or going backward, so keeping it out of equilibrium, which is essentially the starting point, and then removing the perturbation and looking what happens. Both things can be done. So we expect that given a thermodynamic macroscopic quantity x for finite system, it fluctuates around its average value, that with fluctuation that scales like n to the 1 over the square root of n, where n is the number of particles. So we expect a kind of Langevin equation with some forcing eta, which is in average 0 and has a certain amplitude. And clearly, as usual, we can relate this Langevin equation to a Fokker-Planck one, like this, where this is the current and it is related to the drift and the fluctuation part. I used here quantities with the tilde so that now I can insert quantities without the tilde at the end. And now, clearly, near equilibrium, we expect that the probability distribution is given by the Boltzmann one, these things, where U is the potential, which is also related to the force F, which drives the system to equilibrium, by the fact that F is minus the gradient of this potential. We also assume, since we are doing all these kind of comparison between fluctuations and random walks, that fluctuations are related to temperature by the Einstein relation. And so we can essentially express the drift as proportional to the derivative, the gradient of the potential and the temperature. And so essentially this is our Langevin equation. And since at equilibrium we expect that for the equilibrium value, the essentially this potential this is a minimum, is essentially free energy. We can develop the potential near the minimum. This is the internal energy, essentially, and we get the expression for the susceptibility, the real part of the susceptibility associated to a given variable x. So the goal of all of this is to establish a language in the relationship between the standard concepts of a random walk and the fluctuations of any thermodynamic variable. And therefore, we get this equation for the expectation value of for the expectation value, for the value average value of our thermodynamic quantity, which is essentially the relation that we already have seen about an overdamped oscillator without essentially the inertia term and a random force. In order to go on, we introduce now the Hamiltonian formalism in order to be able to explicitly insert the perturbation. So we consider a system defined by an Hamiltonian H function, clearly of the canonical variables Q and P, and this is the probability distribution in the canonical ensemble. Beta is the inverse of temperature, and Z is again the partition function related to the free energy, and this is the volume in phase space where we also inserted the identity of particles. And now we want to perturb the Hamiltonian adding a constant term with that we write as h times x. H is the thermodynamical force conjugated to the dynamical displacement. So, for instance, pressure, volume, or entropy, temperature, all of these are conjugated variables. Now, a new partition function is this one, with so essentially corresponding to a different free energy, and deriving with respect to h, we obtain this. So deriving this and the other one, we get these expressions for which we can get the derivative of the free energy with respect to the external field, which as usual gives the value of the expected value of the conjugated variable. And as I said, this technique can be applied to any pair of thermodynamic variables like magnetic field magnetization, temperature and entropy, pressure, volume, chemical potential, number of particles, etc. In the limit h going to 0, one gets, as usual, the equilibrium value. And this procedure can be iterated in order to obtain the susceptibilities, which is the response with respect to the conjugate force. So the susceptibility is the second derivative of the free energy. So essentially this is the derivative of the expected value of the conjugated variable with respect to the field, and this can be expressed in this way clearly. Then we have to take the limit h equal to 0. So we can perform the derivative, and so we get this variable x plus some constant, plus when we derive the the partition function, this expression here. So essentially we see that the susceptibility is again related to the essentially the variance of this quantity. So for instance, for magnetization, we have this relationship between magnetic susceptibility and the variance of the magnetization. Now, let us consider a time-dependent case in which we have this perturbation that is switched off at t equal to 0. So it is kept constant up to t equal to 0 and then switched off. So up to time t equal to 0, we have to compute the system, but so the equilibrium value of our variables, but using the perturbed Hamiltonian. While when we set h equal to 0, it relaxes to equilibrium. Now, clearly, we use, as usual, the linear approximation, so we assume that the probability distribution changes slowly, and so this time behavior of the expectance value of a quantity is given by okay, we are now just inserting the expression for the average value. This is the partition function of the perturbed system, and clearly this is not an equilibrium value because it depends on time. And clearly we have inserted here the zero value of this variable. Now we can exploit the fact that for small h we can essentially express the exponential by keeping only the first term. Then now we divide both terms by the partition function at equilibrium, so in order to have the equilibrium values. And so we get this expression here, where now the angular brackets denote equilibrium values. Then again, by developing the denominator at first order in H, we get this expression here, which means that the relaxation to equilibrium again is given by the this autocorrelation function times minus the variance. And so for simplicity, let's take the case in which the expectation value is 0. And so this is the condensed form of the relaxation. So essentially, the relaxation to equilibrium depends on clearly the perturbation and the autocorrelation of the values of this variable. And clearly, we expect that the value of a time-dependent observable depends linearly on the response function. We have already met this, like here. In general, we expect that also the variation with respect to the asymptotic value depends linearly on the response function. So essentially, this is the development, the expression of a function with respect to green functions. And again, we can introduce the Fourier transform, the Fourier transforms. The Fourier transforms of the convolution of the product is the product of the function and vice versa. And so, again, we get that the variation of a Fourier transform of a variable is the product of the complex susceptibility and the Fourier transform of the perturbation. And now, finally, we can introduce the real and part of the complex susceptibility. And the imaginary part is given by the difference between the conjugate and the function. So essentially it is given by this expression here. So it is by inserting this anti-Fourier transform, we see that it is related to the part of the response function which is not invariant under time reversal, no? Because if this is equal to this one, they are symmetric with respect to time reversal, but clearly this gives 0. And so what is not invariant under time reversal is the dissipative part. And so essentially we see that the imaginary part of the response function is related to the dissipative or absorptive part of the response function. Essentially, we are, remember that we already have seen something like this, because we have seen that the power absorbed by a system is related to the imaginary part of the response function. And clearly also the power dissipated by a system is related to this imaginary part. And as said, it is an odd function of the frequency. The real part now instead is invariant for time reversal, and it is called the reactive part of the response function. And it is an even function of omega. We are recovering in general form what we have already seen for the harmonic oscillator. Okay, now let us insert the main point, the fact that the future cannot affect the past. So essentially, we have to assume that this response function is 0 for type prime greater than t, so when this argument is negative. This one. Oh, now since this real part is the Fourier transform of the complex response function, we can compute the integral, assuming clearly that the frequency is a complex variable. So to close the integral along the real axis of the complex plane. So clearly this is a real integral, but instead of performing just this real part, we can close the integral in the complex plane. And we use so this is the part, the imaginary axis, and this is the real axis. We close the integral in the upper complex plane, and so the imaginary part is greater than 0, and we know, and we know we derive essentially. So since in order to have this equal to 0, since it is this integral, it is necessary that the complex susceptibility has no poles in the upper part of the complex plane. And indeed, we have seen that for the forced damped oscillator, poles are always in the lower part of the complex plane. So essentially, we see that this is needed in order to have a causal dependence from forcing to response. And we can, with some effort in complex analysis, derive also a relationship between the real and imaginary part coming from this consequence of the response function. And these are called the Kramers-Kronig relation. And another way of saying that real imaginary part of a complex susceptibility are cosine and sine transform of the same function, which is 0 for t less than 0. So in order to proceed analytically, let us consider this function, which resembles the Cauchy integral formula, which is this one, and the Cauchy integral formula is this one. So you see that essentially we have the same part and we miss this part. And the Cauchy integral formula says that if I take a point and I perform an integral in anti-clockwise function around this point for any given radius r, I get of this function, I get the value in this point. Now, we take a contour like this. Clearly, we don't have poles in this region due to this one, but we have one pole here in omega because of the denominator. So I know that there are only one poles here. Now I have to perform this integral here, and this integral essentially has to be considered as a Cauchy principal value. I mean, I'm performing the limit of approaching here and here this pole at the same time, because clearly if I go first from one side and then from the other, I can get essentially an infinity or any value. And also at infinity, I'm going also to infinity with the same say pace. And clearly now I assume that this quantity goes to 0 when the radius of this circle is large enough. So I, in order to compute this integral on this line, I have just to compute what happens near this pole, because the integral on all this circuit is zero. So this one is equal to minus of what happens for this semicircle here. And the idea is that this semi circle here is half of the circle around this pole. So it is half of the Cauchy integral with a minus sign because I'm performing the integral in the clockwise way instead of anti-clockwise ways. So at the end, I obtain that the principal value, so this limit for this integral with the same, say, variable going to zero here, is equal to, for bringing this to the other side, to this quantity. Essentially, by reformulating, I obtain that the complex susceptibility is, say, expressed essentially in a self-consistent way as the principal value. That means integral going at the same pace from minus to plus the pole of this quantity here times something. Now, the important point is that here I have the imaginary unit. So it means that the real part of this goes into the imaginary part of this, and vice versa, the imaginary part goes into the real part. So essentially, the real and the imaginary part of the susceptibility function as related. And so this is the definition of the principal value. Clearly, I can also perform the integral in other ways, and at the end we shall see another derivation of the same formula. So the other possibility is to take the circuit above, or to move the pole below the real axis and then take the limit. So, coming back, these are the Kramers-Kronig relations that essentially relates imaginary and real part of the complex susceptibility together. And as we shall see, these are not just mathematical curiosities, but can be used to derive important consequences. Okay, as I said, there is a simpler, in my opinion, way of deriving the Kramers-Kronig relations that use the Hilbert transform. Now, the Hilbert transform is essentially the real part of what we have seen. It is the convolution of a function with 1 over pi x. So essentially this integral here, which resembles a lot what we have already seen. But these are real, so this is the real part of the functions. Now, the passing in reformulating the same thing in the frequencies, we can see that the Kramers-Kronig relation can be simply seen as minus I times the Hilbert transform. So says that the complex susceptibility is somehow invariant upon this Hilbert transform. Now, the Fourier transform convolution is product of transform, as we have already seen. And the Fourier transform of 1 over x, or 1 over t, is minus 1 pi sagnus of omega. Let's illustrate. I take just the Fourier transform of 1 over t. Instead of computing this, which is difficult, I take the derivative with respect to omega, and which is quite nice because this t goes away and I simply get this, which is a representation of the delta function. Now, if the derivative of something is a delta function, it means that this things is a kind of a heaviside function, so a sine function. And clearly plus a constant, but the constant goes to zero because when omega is large, these things goes to zero because this is an oscillating function. And and so this is a way of saying that the Fourier transform 1 over t is this quantity here. Now we can anti-transform these things here, obtaining these things here. So uh, we started from saying, okay, I want to compute these things here. Okay, but this is seen as the Fourier anti-transform of something in real. Now, if I go backward from Fourier to anti-transform, means that this response function is multiplied by I pi for t less than 0 and by minus I pi for t greater than 0. Because this is the sine function. Now, due to causality, this has to be 0 for t less than 0, and therefore I only get that when we again Fourier transform, we get the susceptibility multiplied by minus I pi, and because of this sign I only take 1. So essentially this disappears and I only have 1. And these are essentially the Kramer-Kronig relation. So essentially it is some way a more direct way of saying that if this response function is 0 for t less than 0, then we have this relationship between the real and the imaginary part of the complex susceptibility. Why it is interesting? Because we can turn on a perturbation at some time, and we have some response of some observable. And the relation between h and x is given by the susceptibility. Now, the susceptibility, the real part, is given by the derivative of x with respect to h, and this is given by the principal value of the imaginary part of the complex susceptibility divided by omega prime. And we have already, which is not surprising, but since we have already seen that this part is related to the power absorbed at this frequency, this is the relation that we obtained before, we can say that if we can measure the absorption of, of a system or the dissipation of a system at all frequencies, and sum all of them divided by the frequency, we can determine the susceptibility of something at zero frequency, which is how a system responds to a perturbation. And this is called the thermodynamic sum rule, and since it is quite easier to measure the absorption, because essentially it is a calorimetric measure with respect to a response that can take a long time and so be disturbed by all fluctuations and so on, this is a useful relation to be exploited in practically. Okay, this concludes this first part of the course.